So now that you guys have learned how to write the longhand electron configuration, I'm now going to make your life a lot easier by teaching you the shorthand electron configuration. So basically what the shorthand electron configuration allows you to do is skip a good majority of the electron configuration you would normally write, have a new starting point, and then keep going from there. So let me show you an example to make it make sense. The shortcut we use is we actually use a noble gas. And so what you're going to do is you're going to find the noble gas from the row that is above the element you're trying to write the shorthand electron configuration for. And you're going to put that symbol in brackets. Then you're going to just keep writing the electron configuration. So let me show you 4 different examples to make this make sense. So let's start with lithium. I'm going to look at my periodic table. Okay. I've got my element that I'm concerned about right here. So I'm going to move up 1 row and move all the way across to the noble gas. Well, the noble gas is going to be helium. So I'm going to go back down and I'm going to put helium in brackets. That's my first step. Okay. Then it says write the electron configuration from there. So I am starting at helium and then I'm going to keep going. So I would just write the next part of the electron configuration, which would be just 2s1. So I'm going to write that. So if you notice, this doesn't really seem like much of a shortcut because all I would have had to have written for lithium is 1s2, 2s1 for the electron configuration. But notice the helium in brackets, by putting it in brackets, I'm saying, hey, I've already covered the 1s2, we've got that covered. Okay? So while that might not seem like a shortcut, let's look at the next example for a better shortcut. Let's look at magnesium. So just like the instruction said, I am going to find my element. I'm going to move up a row, and I'm going to move all the way across to the next noble gas, which is neon. So now I can put neon in brackets and then just keep going. So if I'm starting here at neon, what would the next part of the electron configuration be? Well, it would be 3s2. So I'm going to write it and then explain why that is a shortcut now. So neon is in brackets, and then 3s2. Okay, so why exactly is this a shortcut? Well, now, instead of having to write 1s2, 2s2, 2p6, all I have to do is write neon in brackets. And by putting neon in brackets, I'm saying, hey, I'm including this 1s2, 2s2, 2p6. Let's now keep going by then putting 3s2. So it's a nice shortcut. All right, let's look at the next one. Gallium, Ga. So I got gallium here. Okay. So I'm going to move up a row and all the way across. Okay, so I'm going to put argon in brackets. And then it's just going to be 4s2. That's 4s2. 3d10, and then 4p1. Okay, so I'm going to write that out. So it'll just be argon in brackets, 4s2, 3d10, and 4p1. Okay. So by putting argon in brackets, what I can do is I've actually been able to eliminate having to write my 1s2, my 2s2, my 2p6, my 3s2, and my 3p6. So now that's looking more and more like a shortcut because instead of writing all of that, what I can do is just write argon and then keep going by putting the 4s2, 3d10, 4p1. Okay? Let's look at the last one, tin, Sn. Okay, so let's find tin to begin with. Let's move up a row and across. And I get krypton in brackets, and then I'm going to keep working. So then if I count, remember this is the first energy level, second, third, fourth, fifth, sixth. Okay, so if I start at krypton, this is going to be 5s2, 4d10, okay, and then 5p2. So I'll write this out. Kr is going to be in brackets. 5s2, 4d10, and 5p2. Okay. One quick note before I move on to valence electrons. Notice none of the elements that I've been looking at have been within this transition metal part. So the question becomes, okay, what if I have iron? Where do I look? Well, remember, you're going to move just up one row and across. So you would start with argon in that case. Okay. Or if I had silver, I would move up and then I would move across. So at the beginning of discussing electron configurations, I had talked about the value of it because it allows you to anticipate how an element will react. Well, now we're going to get to why exactly the electron configuration helps you. And in order to understand that, I need to discuss what valence electrons are. Now, valence electrons are your electrons that are in your outermost energy level. Okay, so let's see what that actually looks like with my 4 examples. So here, remember, because I've written this in shorthand electron configuration, I have not included the rest of the electron configuration, which is actually fine, but just for me to make a note for you to see, this would have been 1s2, this would have been 1s2, 2s2, 2p6, and this would have been 1s2, 2s2, 2p6, 3p6. Okay, just for reference, not that it's going to affect us at all. And then you kind of get the point. So remember, I just told you that valence electrons are your electrons in the outermost energy level. Okay, so let's look at lithium for an example. Okay, the outermost energy level, we're talking about the highest principal energy level. So if you look here, I've got 1s and I've got 2s. So 2 is my highest energy level, which means lithium is going to have 1 valence electron. It's as easy as that. Okay. If we look at magnesium, we've got 1s2, 2s2, 2p6, 3s2. Notice 3 is the highest energy level. So I'm going to have 2 valence electrons. Okay. For gallium, 1s2, 2s2, 2p6, 3s2. So notice I can actually ignore this part, right? The 1s2, 2s2, all the way to 3p6, because those are lower energy levels. So if you keep it in shorthand electron configuration, you're fine. The highest energy level for gallium is 4. Notice I have a 4 for 4s and a 4 for 4p, which means what I have to do is add up the total number of electrons here to find the number of valence electrons. So 2 plus 1 will give me 3. Okay. For tin, my highest energy level is 5. So I've got 2 from 5s. I've got 2 from 5p, which means tin has 4 valence electrons. Okay? And it's as easy as that. So what we're going to do, once we've gotten comfortable identifying the number of valence electrons, we're going to discuss how that affects what atoms are willing to do with their electrons, whether it's share them, lose them, or take them away from another element. So in order to understand what atoms will do with their electrons, I need to discuss the octet rule. And what the octet rule tells you is that atoms are most stable when they have 8 electrons in their outermost energy level. Another way of saying this, because the electrons in your outermost energy level are your valence electrons, atoms are most stable when they have 8 valence electrons. That is the ultimate goal. Okay? Well, there are naturally atoms that will have that stable, what we call octet, and those are your noble gases. So if you notice in this diagram here, I'm going to quickly write out the electron configurations that we see. So Notice I've got first energy level, second, third, and fourth. So what these diagrams are doing is they're actually combining orbitals together. So what this would be written out, the electron configuration, is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6. Okay, so let's make sure we see how that's represented. Okay, first energy level has 2 electrons, 1, 2. Okay, second energy level in yellow, you can count it out, they're 8. In the third energy level, it's got 18, which is consistent with this electron configuration. So we've got 2 from 3s, 6 from 3p, and 10 from 3d. And then for the fourth energy level, it's got 8 again, which is 8 in its outermost energy level. So krypton here has 8 valence electrons. Okay, xenon here, if we write out the electron configuration, 1s2, 2s2, 2p6, all the way out. I'll write it super quickly. Notice the first energy level has 2 electrons. The second energy level has 8. The third, you can look at the diagram and look at my electron configuration. The third has 18. The fourth has 18 as well. Okay. And the highest energy level there, which is 5, has 8 again. So at this point, I'm hoping you'll take it from my word. All of the noble gases have 8 valence electrons. And you might be saying, whoa, 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 whoa. Actually, I see a diagram where there aren't 8 valence electrons. And you are right. Helium is always the odd man out. It has, because it only has that first energy level can only have 2 electrons. So helium is actually stable with just 2 valence electrons. Okay. Well, why did I go through all of this? Noble gases are stable. And all atoms want to have the electron configuration of a noble gas. That is when they will be most stable, and that is their ultimate goal, if atoms were to have a goal, is to be stable. So how exactly can they achieve that? Well, let's figure it out. So if we look at our periodic table, let's look at the first column. Regardless of the principal energy level, all of these elements will have 1 valence electron, okay? No matter what. Remember, the electron configuration of hydrogen is 1s1, so that would be 1 valence electron. Lithium, remember, is 1s2, 2s1, so it has 1 valence electron because 2 is the highest energy level. If I went on to sodium, its electron configuration would be 1s2, 2s2, 2p6, 3s1. So it would have 1 valence electron, okay, and so on and so forth. So all of the elements in the first group have 1 valence electron, okay? If you look at the next group, the electron configuration for beryllium is 1s2, 2s2, so it has 2 valence electrons. If you wrote out the electron configuration for anyone in this group, they would all be 2 valence electrons. And if you notice, we're going to start to have a trend. We're going to skip the transition metals. If I wrote out the electron configuration for boron, for example, it's going to be 1s2, 2s2, 2p1. Okay, and if you count, that's going to be 3 valence electrons. So what you should notice, I've got 1, 2, 3. As you move across, the number of valence electrons increases until you reach your noble gases. And we had already said your noble gases have 7 valence electrons. Okay, and remember, the goal of every atom is to achieve the electron configuration of a noble gas. Okay, so let's talk about how that can be done. All right, I'm going to start on the right-hand side, and then we'll go back and look on the other side. So here, for my group with fluorine here, they have 7 valence electrons. Well, what can they do to get 8 valence electrons? Well, they can gain a valence electron to get the electron configuration of a noble gas. So fluorine, for example, which is 1s2, 2s2, 2p5, all it has to do to get the electron configuration of neon is it has to gain 1 electron. And then it'll be 2p6, and there'll be 8 valence electrons. So if it gains an electron, that means it will have a -1 charge. So all the atoms in this group, in your halogen group, will have a -1 charge when they form an ion to be stable. Oxygen, which has 6 valence electrons, and anyone in its group, how can it get 8 valence electrons? It can gain 2 valence electrons. For the next group, with nitrogen's group, what can it do? They can gain 3 electrons. So these are the charges of the atoms when they form ions. Okay? Let's go back to group 1 and look at hydrogen's group. Okay? These guys have 1 valence electron. So using the thought process we just went through, they would need to gain 7 electrons in order to get an octet. Or, if you think about it, let's look at sodium really quickly. Sodium's electron configuration is 1s2, 2s2, 2p6, and then 3s1. Well, it would have to gain 7 electrons, or if you notice, if I just got rid of the 3s1, I now will have 2 plus 6, I'll have 8 valence electrons, and so it will have the electron configuration of a noble gas, and it will be stable. So what metals do on the left-hand side, instead of gaining electrons, they actually lose electrons. So the charge for group 1 is going to be +1 because they're losing 1 electron. Okay? Group 2, how many valence electrons does it need to lose? It needs to lose 2. Okay? If we look at, for example, aluminum, to figure out the charge for that group, it has 3 valence electrons, remember? So what I can do is simply lose those 3 valence electrons in order to have 8 in the new outermost energy level. And so these guys will have a +3 charge because they're going to lose 3 electrons. So valence electrons counting. As you move across the periodic table, okay, group 1 has 1, group 2 has 2, go over to boron's group, 3, 4, 5, 6, 7, 8. For charges, group 1 has a +1 always, group 2 has a +2 always, group 3 has a +3. Notice we skip group 4 or group 14 simply because it's not that simple when you have 4 valence electrons, because do you gain 4 or do you lose 4? So they do not achieve a normal, regular, reliable charge. We'll talk about that later. Okay, so +1, +2, +3, skip, -3, -2, -1. And what do you think the charge for your noble gases will be? Well, it would be 0 because they don't want to gain or lose any electrons because they are stable already. Okay? And that's it.